Thank you for the introduction. So recent advances in artificial intelligence, in AR and VR technologies are gradually enabling humans and virtual agents to coexist, co-work, and share spaces in different environments. And it's becoming more important for technologies to model people, their behaviors, their interactions, their motions, and their emotions for a variety of different applications, including virtual reality applications, healthcare, games, or even social robotics. So today I'm going to talk about how we model them, these agents, to be more human-like, and how these agents can express just like us. So with the rise of mass market devices, virtual reality is becoming more commonplace. There's a new rise of social VR where people are exploring these virtual worlds with other people as well as other intelligent virtual agents. And we have also seen a massive increase in virtual reality in the healthcare sector, like training doctors or virtual therapists. I recently read that 1/5 of all Facebook employees, or now Meta employees, are working on AR and VR projects, and some estimates saying that Microsoft will spend around $22 billion just working on AR training applications with the military. And I'm sure if you've all followed up the latest metaverse related developments. So obviously I am biased, and if you ask me, we are at the junction of a very big potentially very big virtual AR and VR revolution fueled by these intelligent and functional virtual agents. Okay, with all that motivation aside, let's just dive into virtual humans. So just a quick heads up, I'll be using the term agent a lot, and depending on the application, an agent may mean different things. For this talk, it broadly refers to a virtual character. All right, so as we interact more and more with virtual agents in everyday lives, it becomes more important to make sure that these interactions are believable, thereby enhancing the overall experience. So my group's research goal, or our research goal, is to model these human emotions and behaviors for this virtual human-like agent, but to also assist and enable a more natural, a more interactive, a more collaborative, and a more behaviorally aware human agent interactions and locomotions in the virtual world. So before jumping into modeling these digital or virtual emotional and behavioral expressions, let's look at how we humans express affect. So affect is the scientific term for emotions, and it's commonly represented as either discrete categories or continuous dimensions. So discrete categories consist of emotion terms that we are fairly familiar with in daily conversations, right? So happy, sad, angry, surprised, bored, and so on. While these terms are, may be easy to understand intuitively, they're fairly hard to define rigorously. On the other hand, continuous dimensions tackles this problem by describing emotions uh, using three fundamental properties of valence, arousal, and dominance, and representing these emotions as points along these three principal dimensions. So valence indicates how pleasant or unpleasant an emotion is. Arousal indicates how much the emotion is tied to high or low physiological intensity, and dominance indicates how much the emotion sort of imposes on the observer. So let me give you an example. So a discrete emotion term such as happy or happiness indicates a high valence, a medium arousal, and a medium dominance. Something like anger or angry would indicate a low valence but a high arousal and a high dominance. And on the other side of the spectrum, something like sadness indicates a low valence, a low arousal, and a low dominance. And more recent studies have also shown that these specific VAD values, or valence, arousal, dominance values, can be assigned to the discrete emotion terms, making it fairly easy or convenient to traverse between the two representations whenever required. So emotions are perceived from multiple cues and modalities, and the most widely studied modalities are in the field of affective computing are from faces, speech, and written text. However, there's a lot of recent psychology studies, or in general studies in affective computing, that have shown that body expressions play a very important role in the perception of affect. For example, in this study, they showed pictures of tennis players after winning or losing a match. I know this would have been a live experiment for all of you if you were in person, and I was there. But let's just, while sitting on our Teams Zoom screens, let's just try to figure it out in our head. So what do you feel about player one? Do you think player one won the match, or do you think player one lost the match? What about player two? So I'll give you 5 seconds to think about how you feel about these players. So these are essentially pictures of tennis players after winning or losing a match. 5 seconds. All right. Let me show the results, and in your heads, just calculate how many of them you got them right. Right. So player one lost the match. Player two won the match. So on and so forth. So, clearly, again, just based on my previous experience from this talk, there is a lot of confusion when it comes to understanding the emotion behind just the facial expressions, right? I mean, I'm presuming many of you got one or two or three of them incorrect. Now, in the same study, they also showed pictures of just the body expressions. Now, can you guess whether player one won the match or player two won the match? So player one won the match and player two lost the match. Um, Clearly, this was a much more easier question, and I'm hoping most of you got it correctly, or at least partly correctly, right? So the participants' responses in these studies also showed a very similar trend. This demonstrates that body expressions are essential in affect modeling. For me, or for us, this work was a very big motivation for our research on body expressions, which have been relatively unexplored in this affective computing realm. So body expressions or body language for virtual agents is essential to convey naturalness and ease interaction. So in short, to make these agents more trustworthy. So we have developed or are working on multiple such body expression generation approaches. In the interest of time in this short talk, I'll be focusing today on just the first two, the gaits and the gestures. So let's start by looking into gaits. So in this work, we focus on the problem of generating emotive walking styles or gaits. So studies in affective computing indicate that humans observed physiological features such as arm swings, stride lengths, head jerks, upper body postures when attempting to perceive the other person's emotions. So these features are collectively called as affective features. And to classify the gaits into different emotional spectrums, our goal is to train a machine learning model that can leverage these social psychology inspired affective features. So before I introduce the full approach, let's look at two different types of affective features that we need to synthesize emotional expressions and at the same time generate plausible movements for the virtual agents. So prior work in social psychology, we use multiple affective features as we see in these figures. Things from angles at the shoulder, arms, legs, distance ratios, and area ratios. For plausible movements, we train our network to learn from something called movement features. So these are features computed from the agent's root joint, which is relatively stable with respect to the rest of the body and its trajectory. And it determines more or less how fast the agent is moving and in which direction. So in things include like route height from the ground plane, the orientation of the route, the stepping phase and the stepping frequency, where the stepping phase determines the elevation of the feet between the footfalls, and the stepping frequency is its time derivative. So let's formulate this problem as a sequence prediction task, and we learn the conditional distribution space as a neural network. So the neural network function is represented by the function f. It takes in motion history as input and is conditioned on the emotion labels E. Um, so for optimizing the network, we prefer a loss function using distance metric between the predicted and the target motions as per the data, as well as their time derivatives or motion velocities. To better constrain the loss, we also add regularizations in the form of differences between the intermediate features, such as the affective and the movement features. All right, so we use a variety of different publicly available data sets of walking gaits, including many data sets we ourselves released. So either they are motion captured or extracted from RGB videos using computer vision pose estimation methods. So with that background, let's look at the full pipeline. Given a short history of a virtual agent's gait, the intended future trajectory, the intended emotion, and the affect and movement features computed from those gaits, our goal is to synthesize the gaits of the virtual agents on a real-time trajectory while expressing a specific given emotion. So we formulate this problem as an autoregression problem, where we are predicting or generating a future sequence of poses from a past sequence of poses. And to solve this, we solve this using an encoder for the past data and a predictor for the generated future data. So our encoder learns separate latent representations for the root joint and other joints. This is because the root joint is relevant for the trajectory, the actual movement, whereas the other joints in the body are relevant for the emotional expressiveness. So to predict the future trajectory features, we combine the affective features, the emotion labels, the past trajectory, and the root features using a set of fully connected layers in our encoder, and then predict using another set of fully connected layers. To predict the future forward kinematic parameters for the other body joints, we use a temporal network such as the GRU or the gated recurrent unit to efficiently learn the high dimensional data and predict using fully connected layers. So we train this network using a combination of different losses, which in the interest of time, I'm not going to go into the depth, but essentially to make sure that our motions are smooth, kinematically valid, and emotionally expressive, and to eliminate things like foot sliding. So let's look at some qualitative results. So here we see an emotionally expressive gaits for virtual agents walking on real-time user-driven trajectories. We see the outputs of four basic emotions like happy, sad, angry, and neutral. We also see the results of performing transitions between the different emotions. So we can generate smooth and plausible transitions from the expressions from one emotion to the next as the agent keeps on working on real-time user-driven trajectories. All right, so on to the more boring part of the paper. So we conducted user studies with our synthesized gates. For the first user study, we tested the null hypothesis that the intended emotion and the perceived emotion for each of these synthesized gates are from the same distribution space. So as we can see from an excerpt of results here, that with a 95% confidence interval, we cannot reject the null hypothesis in about 90% of the synthesized samples. So we also look at the intended and the perceived emotions, and we observe that the samples closely match in most cases. For our second study, our objective was to validate the choice of these post-affective features. These are the features we sort of borrowed from social psychology into our paper, and we want to validate whether the choice of these features for the virtual agents, were correct for the virtual agent's emotion expressiveness. So for this, we obtained the values for the post-affective features observed by the participants from the synthesized gates on a 5-point Likert scale. So in this figure, you can see rows that represent different emotions and the columns representing different broad post-affective features. So the horizontal axis for each column denotes the Likert scale choices for the corresponding feature, with labels ranging from contracted to expanded for torso and the arms, the upper body, the slow to fast when it comes to the gait pace, and erratic to smooth when it comes to gait flow. Um, so we can see from the results that the participants vote for the broad affective features have distinct modes for these different emotions, sort of indicating that the post-affective features vary between different emotions, but are consistent across observers for a specific emotion. So to summarize, we presented an autoregression method to generate emotive gates using user-driven trajectories. Our emotion model is based on a combination of categorical emotions, and we can smoothly switch between different gates and different emotions. Obviously, we have a lot of limitations to our method, and even to the best of our knowledge, this was the first method to synthesize gates with a desired emotion expressiveness. Uh, our limitations vary from, we have a lot of limitations. So the first being our formulation considers a sort of linear space of the representative emotions. In the future, we want to, of course, extend it to three dimensions VAD space, which we discussed earlier. And right now, we only look at affective and movement features to generate gates. It would be really useful to incorporate information corresponding to other modalities, such as the context of the context of the person walking, the context of the gate into our generation model itself. All right, from gates, let's move on to the next form of body expressions, gestures. So we want our agents to emote during a conversation. So we humans, we naturally produce these rich gestures spontaneously without effort. However, to obtain an automatic generation of gestures in these agents, there are several fundamental issues that must be tackled. So, what are gestures? Especially, what are co-speech gestures? So, these are bodily expressions associated with a person's speech that help us underline the subject matter and the context of the speech. So, broadly speaking, there are four different kinds of co-speech gestures. There are the beat and the dialectic gestures that are used for regular rhythmic movements, such as pointing to people, pointing to objects, as we can see in this short example.
Today, I'm going to talk about race, and I'll start off by sharing with you my story of growing up Asian American.
Iconic gestures are used to express physical concepts or actions.
Make your bed, they brush your hair, they do small artwork, they do handshakes.
And last but not least, metaphoric gestures that describe the abstract concepts such as emotions or affect.
Was very sorry to tell me that I had breast cancer.
So there's a lot of prior work in this area, but they've mostly focused on synthesizing or generating high quality gestures with individual speaker styles. And they focus on things like the beat, didactic, and iconic gestures associated with the speech content. In our work, we focus primarily on the quality of the metaphoric gestures for different affects and emotions in this core speech gesture synthesis pipeline, while still maintaining the quality of the other kinds of gestures. So affective co-speech gestures are not only infrequent, but they vary significantly based on the context of the speech and the content of the speech, based on the individual speaker styles. At the same time, affective gestures are a crucial component in human agent interactions as the listener's experiences and reactions are often shaped by the perception and of the speaker's affect. So studies in affective computing show that gestures are very good indicators of arousal and dominance. Unfortunately, different valence levels, at least according to our research, have not been generally associated with consistent differences in gestures and are often inferred from other cues and contexts. So emotions such as high arousal, such as amusement, tend to be expressed with rapid arm movements, head movements. In contrast, emotions with low arousal, such as sadness, tend to be more or less expressed with subtle and slow movements. Again, emotions with high dominance, such as pride, tend to be expressed with an expanded upper body, spread arms, upright head positions. On the other hand, emotions with low dominance, such as fear, uh, usually are expressed with a contracted upper body, arms close to the body, and collapsed head positions. So again, similar to what you saw for gates, we have a set of gesture-based features, but we only consider the more upper body parts of these affective features where gestures are more or less expressed. So the major contributions in this specific work is we aim to synthesize co-speech gestures that follow the individual styles of gesticulation. So we do not assume the availability of intended emotions, and we rather learn the desired emotional expressiveness directly from the speech and gestures. So let's look at one of the synthesized samples to see what this means.
Out into a wider space beyond. I was, I believe, ecologically bored.
So here we see the speaker's arm movements matching his frustration on the word board. So let me play this video again so you can see.
Out into a wider space beyond. I was, I believe, ecologically bored.
So I want to emphasize that in this particular project, we are not looking at finger movements yet. A separate problem we are working on right now. You saw a glimpse of it in the initial slides. So just look at the gestures from the upper body without the fingers. And fingers are a much harder problem to not only synthesize but also capture data from the real world where we are learning all these things. So we'll take a brief look at that later. So to be able to synthesize such affective gestures, our key contribution is to learn an efficient set of latent affective features based on these body postures, head positions, and arm motion. And I'll give you, a simple example of what I mean by these three different poses, uh, in the talk later on. To synchronize the affects of the synthesized gestures with the affects in the input speech, we designed something we call the MFCC encoder, or the meld frequency Keptral coefficients encoder. So this encoder maps a speech-based affective cues such as prosody, tone of your voice, intonation of your voice, to learnable latent features and to guide the gesture synthesis. I'll give you a simple example of what I really mean by um, you know, how we can capture differences in emotions while looking at these speech features. So, and also like hand body expression features. So, sometimes we ask our friends and family, how are you feeling? Now, people can say the same answer even with the same exact content of the speech. So look at me. So I can say, I'm feeling okay. I'm feeling okay. Or they can say, I'm feeling okay. So even though the content of the speech was exactly the same, the two I am feeling okays were very different in the emotional spectrum they're coming from. In the first case, clearly that person is okay. And in the second case, we're not so sure. Something might be bothering this person, or something might be saying, thinking of something else. So definitely there are two different versions of the same content depending on how we say things. What are different speech features from this? What is my body language? So we try to combine all of this information in order to have a model which is more efficient in gesture synthesis. All right, so similar to what you saw for Gates, we also formulate our problem as a sequence prediction task, and we learn the conditional distribution space as a neural network. So the neural network is represented by a function f. It takes speech s and the motion history g bar as inputs and is conditioned on the emotion labels and the agent attributes collectively denoted by e. So for optimizing the network, we prepare a loss function using distance metrics between the predicted and the target motions, between the generated and the target motions, as well as their time derivatives and motion velocities. To better constrain the loss, we also add regularizations in the form of affective features. So similarly, we also use multiple publicly available data sets for modeling our co-speed gesture synthesis pipeline. To synthesize the affective gestures, we need to consider both the source speech and the individual styles of the speakers. Specifically, we take into account the raw speech audio of the speaker or use a speech generator for virtual agent of the social robot, the corresponding text transcript as sort of a complementary information to safeguard against the noise in the speech data, the speaker's unique ID in the dataset, and a short sequence of poses and synthesize the speaker's affective gestures while matching the individual styles. So we use separate encoders to encode the speech, text, speaker ID, and the affective content of the seed poses into latent features. So we use a text encoder based on fast text to encode these words into latent features. We use a speaker encoder to encode the speaker IDs into a latent distribution space. In order to encode the speech, we transform the raw frequency waveform into mel frequency Keptl coefficients or MFCCs and the first and second order derivatives. So MFCCs are very useful for identifying speech-based affective cues such as tone, prosody, intonation, etc. We also design a set of convolutional neural network layers to obtain the latent features from these MFCCs. Again, I want to emphasize here that MFCCs are not dependent on the actual words of the speech, rather the speaker's verbalization of those words. We also design an affective encoder which takes into account the pose sequences and then transforms them into latent gesture-based affective features. So to achieve this, we learn from the body movements at two different levels of hierarchy. So the first one is at the level of the individual bones, where we encode the relative movements of the two bones into feature representation. To capture the relative movement, we consider a two-hop neighborhood of each bone to define their spatial adjacencies. Again, long story short, we consider two bones to be spatially adjacent if and only if A, they share joints like you see, the lines, they are connected to two ends of a third bone, or C, for temporal adjacency, we consider the same bone at two different adjacent time steps in both past and the future. As a result, we can efficiently encode the differences in their relative movements for different affects. To perform the actual encoding, we utilize something which we call this, something which is called the spatial temporal graph convolution network, or STGCNs, which is commonly used for computing features from localized dependencies in graph structured data. The second level hierarchy is the level of the three upper body parts, the trunk and the two arms. So these three upper body parts sort of capture a macroscopic body movements such as raising arms, crossing arms, bending, straightening the trunk. So in the second level, we assume that both arms need to be adjacent to the torso, but not to each other, since the movements of these do not need to influence each other. Again, we consider another temporally adjacency similar to this first, more microscopic level, and we again use an STGCN for the feature encoding. To reduce the dimensionality of the latent affective features, we pass this output of the second STGCN through a set of convolutional layers, capturing the interdependency between these features. All right, so back to our network, to our full network. We proceed to synthesize the gestures from the four latent features we discussed earlier, the text encoder, the speech encoder, the speaker, and the affect, by concatenating them and passing them through a bidirectional gated recurrent unit, or a bi-GRU. The bi-GRU sort of provides temporally related intermediate features, which we then transform into a set of fully connected layers, and we term this entire thing our generator. All right. So, however, just using the generator by itself does not ensure that the gestures we get are realistic. So to achieve that, we need to couple our generator with an adversarial discriminator that can distinguish between original and the synthesized gestures. So we pass the gestures of the synthesized gestures to the discriminator along with the corresponding original gestures of the speaker. Again, we make use of the affective encoder to transform both the gestures into latent affective features to discriminate them based on the affective encoder. So we use a bi-GRU and a set of fully connected layers to transform these latent features into single dimensional variable. So we can more efficiently train the discriminator to optimize these labels using across entropy laws. Correspondingly, the goal of our generator is to synthesize gestures that our discriminator cannot distinguish from the original gestures. So once the generator is fully trained, we can use it to synthesize our desired affective co-speech gestures. So let's look at some qualitative comparisons for our synthesized gestures on the benchmark TED gesture data. So the TED gesture dataset consists of videos of English language speeches at TED Talks. So let's look at an example video in the dataset.
Out into a wider space beyond. I was, I believe, ecologically bored.
So here GTC denotes the gesture synthesized using the prior state-of-the-art. So their method synthesizes gestures based on speech, text, and speaker identity, but not the body expression based emotions. So let's look at the results.
Out into a wider space beyond. I was, I believe, ecologically bored.
So as we can see, our synthesized arm movements indicate an expression of frustration on the word bored. Also, on a side note, we also see that both these gestures, GTC or ours, visually differ from the gestures of the original speaker. This is more or less expected and desired in some cases, since both the methods aim to produce a variability of speaker styles, rather than just faithfully recreating the original gesture. So let's look at some of the more results.
As a product developer, I started my process of research. I was very excited to find that there was a product out there called the Clean Birth Kit. As a product developer, I started my process of research. I was very excited to find that there was a product out there called the Clean Birth Kit.
So in this example, we also see a swift arm stretch on the word, in our synthesized gestures, expressing the speaker's happiness on the word excited. So let's look at this video one more time.
As a product developer, I started my process of research. I was very excited to find that there was a product out there called the Clean Birth Kit.
Okay, so we also compared the quantitative performance of a method with different baseline methods on three fairly common evaluation metrics and two benchmark data set. So the metrics are MAGE, which measures the difference between the joint positions of the generated and the original gestures, MAD, which predicts how closely the joints match the original and the predicted, sort of a good indicator for how expressive our generated gestures are. And FGD, or the fresh air gesture distance, has been shown to align well with the perceived plausibility of the synthesized gestures to human observers. So a lower FGD is desirable to gauge the quality of the gestures. So you can see from the table that our method consistently outperforms the current baselines and on all the three metrics on both the data sets. So again, similar to the last problem we saw, we conducted elaborate user studies in two parts to evaluate the perceptual quality of the synthesized gestures. This is something which is very critical to, the kind of research we are doing in terms of generation in this affective space. We don't really have anything which we can call ground truth to have a more quantitative evaluation, make sense. So we need to make sure that we take our results and do a long user study across different cultures, across different people, even with the same data, to gauge whether there was a broader consensus of our generation. So the first part was to determine how plausible our gestures appeared on a 5-point Likert scale. So looking at the results, we observed that 15.28% more participants preferred our synthesized gestures, either 4 or 5, compared to the original gestures generated by, or compared to the gestures generated by the GTC. More interestingly, or a little bit funnily, about 3.8% participants marked our synthesized gestures 4 or 5 compared to the original gestures, indicating that the participants found our synthesized gestures to have a similar visual quality than compared to the original data. Similarly, a second part was to determine how well the gestures synchronized with the corresponding speeches, again on a 5-point Likert scale. So looking at the results, we again observe that we do 16% better than the previous method and about 4 to 5% better than the original. So you might be thinking, like, why is your method better than the original speak? That's like, the baseline, right? As I mentioned, that we don't have anything, so to speak, as the ground truth. We have variability in terms of speaker styles, or how different people express those things. And we also observe that our method kind of smoothens out some of these trajectory information. So some of that might be from different reasons, but also they are all visually different. So there is no 1:1 mapping between the input audio and the generated text. Sorry, the generated gesture. All right, so to summarize this work, so our work is a generative adversarial network to synthesize co-speech gestures with appropriate expressions. In this specific work, we do not use any explicit emotion labels like the last one, like we explicitly trained our network on emotions. Rather, we learn the appropriate affectiveness or from the speech and the gestures. So we built an affective encoder to learn these latent pose-based affective features, and we designed a novel MFCC encoder that leverages these mel frequency capture coefficients computed from the raw speech to sync with the synthesized gestures with the speech-based cues such as prosody or intonation. Again, our work has many limitations. First, we do not build a mechanism to control these expressions. We compute them automatically from the input modalities. So in the future, we plan to investigate the interface between, the expressions themselves from the speech and gestures especially when expressing things like sarcasm, like contradictory cues such as sarcasm or irony. Second, we plan to use a more finer representation of the pose. As I said, we don't do finger motions at this point, but eventually in the future, we want to have a more richer representation of the human. Obviously, with more, more joints, more representation, the compute cycles go up and up. But that's where the research would lie. That how do we optimize on a much richer or finer representation of the poses? Finally, we just looked at the upper body gestures. There's a lot of gestures which actually come from the lower body part as well. These are usually very subtle, but in terms of a conversation where two people are standing and talking, they have a lot of information which we might be missing out given our present representation. All right, so coming back to the broader research question, in order to simulate interactive and functional virtual agents, we need, we need many ingredients. And what I demonstrated today was just two of such ingredients, specifically two body expressions that we have modeled. To recap, we looked at modeling affect-driven gaits or human walking styles. We also saw how gestures reflect the agent's internal thoughts and how we can model them. In the interest of time, I could cover many other ingredients, including generating hand gestures. So hand gestures help take what's in our mind and make it intelligible to others, and a very key aspect to make interaction in virtual reality more convenient. So far, all the things I've talked about, are more about body expression generation approaches. But to actually enable better conversational agents, we need to build and develop better detection and perception algorithms of these affective states. So beyond the traditional realm of graphics or computer graphics and affective computing, we are working on and collaborating with other AI and vision scientists to model different affect-based perception modalities such as facial expressions, speech, voice modulations, or even context in real time. Again, beyond the generation of characters in the virtual metaverse world, locomotion will play a critical role in the success of large-scale interactive algorithms. So one serious problem with real walking in VR is that the size of the virtual scene is limited by the size of the physical area, right? We all have this, very fancy virtual reality, experiments. We have these experiences, but at the end of the day, we are still limited by our four walls around us. We cannot go beyond these four walls. Um, I have a very small office space in my office at Purdue, maybe a 6 by 6 meters or whatever, and it's almost impossible to, really. How do I say this? Really bring somebody from their office to a virtual space, which, let's say, a beach or their favorite places or something which is a much larger space than the physical limitation. So we have to address this limitation. We've also developed something which is called redirected walking, which is done by interactively and imperceptibly modifying the virtual world to trick the mind of the walker that they are in a much larger space. So in this case, as you see on the video, the person is walking in circles in his or her living room, but in the virtual world, they're walking along a straight line almost indefinitely. So, with these tricks of the mind, small changes in the virtual, landscape, small changes to trick your mind, you can again trick your mind to believing that you're in a much larger space than you actually are. Again, because in the interest of time, I'm not going to go into most of these things in depth, but we've talked about many of these ingredients. But I also wanted to give you a brief glimpse into some of our current or ongoing projects. So all of them in the broader realm of affect modeling and leveraging all of these ingredients I talked about. So we designed an AI conversational agent, which we call Dost, that combines the detection and the generation work to create realistic interactive avatars to have intelligent conversations with real humans. Uh, Again, just an FYI, we haven't modeled the finger motions into this project yet. So you might see something funny happening with the hands, but we're working on it, and hopefully in the next version of this project, I can show you guys a much more realistic looking avatar.
Hello, I'm your artificial intelligence-driven virtual conversational assistant. I can help you with daily chores, tasks, and will be able to make smart conversations.
My gestures, facial expressions, and speech are generated in real time using state of the art research in affective computing, emotional modeling, character and speech generation, and virtual reality.
I was designed at the
And in the interest of time, I'm going to skip over the whole video, but all of these are on our website, which was mentioned below, and I'm more than happy to talk about it after as well. So using those as the baseline framework, this project, my students and I are working on a funded project with the behavioral health experts and psychiatrists with the Maryland Medical School to develop a technological approach to assess a patient's behavioral state and create these virtual humans that can respond in real time using human gestures and emotional cues. The overall goal is to improve patient care and engagement. So our project is looking at people who are at the most risk of depression or who experience disparities in healthcare. We're also working with the Baltimore Police and Google to develop virtual embodiment tools for law enforcement training to reduce implicit racial bias. So we are building these large-scale virtual reality scenarios to train police officers to experience racial bias with embodied characters.
I don't care if this is your first time here. I'm the one who's being harassed.
Sir, is your wife in there? If you have a wife in there, I call about a domestic dispute.
121, just want she's saying she's not in danger.
You have a wife inside the house. Is there anyone else inside the house?
Since we are working with joint level data, right, a lot of our algorithms can be transferred to humanoid-like robots that can eventually inspire trust and desire amongst humans. So we have built a variety of different social robotics or affective robotics where we're generating these gestures which we can put on humanoid looking robots that can navigate the space around us and interact with us. So, our work has won, multiple academic awards in top AR and VR conferences. And we have, been featured by many media houses, including Forbes, Wired, Science, and many others. But what we really want to do in the future, which we really excite us, is there's so many different problems to this whole area, right? So I want to share some of these open problems, open sub problems with you guys, and hopefully in the future, if there's interest in collaboration with folks like researchers like yourself, at least there's I want to put forward all the questions which I want to explore and we haven't been able to explore so far. So one of the immediate things that we want to work on is facial expressions. So extending further from the synchronous generation of speech and gestures, we are working on building a method to generate both facial expressions and emotionally expressive gestures synchronized with the speech. So there's definitely a lot of research questions that we need to address for this. One is to determine a plausible set of affective features for facial expressions to generate highly plausible micro expressions. Another question is to synchronize, like how do we synchronize these micro expressions or expressions in general with the broader gestures? We need to leverage probably other existing image or video data, learn their relationships, and then map those into 3D meshes and joint structures. And last but not least, as we attempt to synchronize these modalities together, we need to be mindful of the resulting uncanny values. which can grow to be larger than the sum of the individual parts. Therefore, we should, again, I don't know the solution to this, but more effective user studies or better models to synchronize these things so that we don't actually worsen the uncanny valley in this problem. So, our approaches can be used to generate human-like characters who can express feeling or empathy, especially during times like these, COVID, for our seniors and elders. So, we wish to continue working with the mental health and virtual therapy with the medical school. At the same time, we also want to build on VR approaches using intelligent agents for virtual rehabilitation, which has been shown, scientifically to improve things like motor, cognitive, and functional outcomes in adult stroke. So we've started collaborations with different departments at Maryland, Purdue, and the National Institute of Aging on a funded project to learn human motion differences with age and health problems, taking into account these biomechanical constraints and then the modeling them for virtual reality rehabilitation applications. So this is like a broad, this is like a motion capture space that we've set up here with sensors that capture not only the facial expression, the gait, which we have talked about before, but also foot pressure. There's a lot of different diseases or health problems as as we age that we can really capture with the actual learning from the pressure on the soles. Of course, this is my student Samantha here trying the system out, but we really hope to start inpatient studies soon. So there are substantial cultural variables or differences in how people use body language to communicate. Sometimes it's subtle, but sometimes it's obvious. So if we really want our virtual agents to talk like us, understand our differences, we have to learn from a diverse set of cultures, races, countries, and genders. So clearly there's a long journey ahead. So, even though we've discussed a lot of this research, all of this is fundamentally reliant on collaborations. We want to not only build on these infinite number of blocks, but understand these connections between these blocks as well. And I believe some really novel research and understanding of the human mind is in this. And to truly understand and build on these collaborations with researchers like yourselves is not just a good thing to have, but a necessity. Most of our affective results you saw so far are based on correlation and not causation. And hence they sort of lack the right actionable insights and models to explain the predictions being made. Because of our group's highly perceptual nature, it's important to collaborate with machine learning groups, researchers to understand, improve explainability and understand causality. Intelligent virtual agents also need to communicate intelligently. So we need to build NLP-based algorithms to complement our agent states, cultures, and other variables. And our research has a wide range of applications in HCI, HRI, to generate model robots that can interact with real humans intelligently and socially. So what we really want, we have worked with many researchers outside computer science as well, including psychology, psychiatry. We've been working on this research for 10 plus years. We have modeled based on many psychology, theories, collaborated with doctors and therapists and psychology, used their gold standards to validate our algorithms. And that's all great. But our group's real hope and dream is that we in computer science, we in affective computing, find newer understandings of the human mind, and we can someday contribute back to these fields. So before I wrap up, I want to conclude with some very final acknowledgements. None of these research would have been possible without my wonderful, diverse, and extremely talented students. A special thanks to all my academic and industry collaborators. And last but not least, I would like to thank my funding agencies for believing in our research and for paying the bills. So thank you so much. I'll take some questions now, or I'm more than happy to take questions over email later.